Thank you to the organizers for the invitation. It's not often that I get the chance to speak to or learn from this kind of community, so thanks. I'm going to give you, I guess, an overview of some of the things you can do with operator-theoretic methods. And so I've got two parts to my talk. There's a part 0 where it's sort of, I added some background to give a bit more context and show you a few more things after seeing some of the talks. And then the main ones I want to talk about are birth and death of these persistent large-scale structures that you can detect in time dynamics. And that's joint work with Alex Badza at UNSW. And then the second part is about extracting climate cycles. So you've seen some of this from Dimitris and Claire's talk. And I guess the very new part to this is identifying maximal sensitivities of climate cycles. And this is joint with Dimitris and Nick Peters. And then I did have this part on machine learning that I deleted due to time, and now seeing all the talks on machine learning, I kind of regret deleting it. But if you want to ask me about that, it's essentially how you learn efficient bases to represent these operators. All right. Actually, Adam talked about emergence in complex dynamics. So you can have, in dynamical systems, you can have complicated dynamics emerging from simple micro rules. And this emergence often takes the form of large, complicated macro phenomena. And it's these macro phenomena that you see and touch in your everyday lives. And one example of that is you might have many small individual particles collectively moving as a group for a substantial period of time. So, for example, if you're doing social dynamics, you might have a large group of people that hold a similar opinion for several years. So you have the large group aspect and you have the time persistence aspect. Or something from earth science, you might in the atmosphere have many air parcels grouped together and they sit over a geographic location for a long time or longer than usual. And this might cause a heat wave. So to access these macro phenomena, I'm going to build linear operators from the nonlinear micro rules, microdynamics. And maybe just an example to put some concrete things in your head. So Adam also talked about Rayleigh-Bernard, so I thought I'd add some Rayleigh-Bernard example. So you've got a 16 by 16 by 1 tank of fluid, and you heat at the bottom, you cool at the top, and if the temperature differential is sufficiently high, you get turbulent convective motion. And okay, let me show you a video. And I'll speed it up so it's a bit more interesting. Yeah, that should do. Okay, so in both cases, I've painted each particle, this is a top view, I painted each particle a color, and the color doesn't change as the particles evolve. On the right, I just put some stripes, and you can see that the fluid is turbulent over some short period of time. But if you color particles differently, like on the left, you see these red spots, and the red spots tend to not dissipate as much as the geometric stripes suggest. So embedded in this turbulent flow are these structures, these large structures that persist for some time. And these are examples of what are called coherent sets. So they're coherent parts of, in this case, the fluid, and they resist mixing and remain coherent. And yes? Yes, I just painted the particles different colors. Yeah. You're not the first person to ask that question. Okay, so how did I build those red spots? So this is our first linear operator. Let's say our state space is M, and my dynamics is, for the first part of the talk, this will be called phi t. So phi is flowing your points for time t. And I want to act on functions on M. So I have some real valued function f on M, and we've already seen the natural push forward, the transfer operator. So this is where you compose with the inverse of phi t. And the pullback, the Koopman operator, where you compose with phi t. And if you're deterministic, then you could write this as the adjoint of the push forward. So now I'm going to take these two and put them together with a Laplace operator to make a dynamic Laplace operator. So this is, again, obviously a linear operator. And so what I'm doing is averaging over this time interval of interest, let's say of the movie that you saw. And what you do is you push forward for t, you apply Laplace in the future, and then you pull back. And you average this across the time interval. And if you're familiar with Laplace eigenfunctions having connections to geometry, then what you're doing here is you're making an operator that feels the average evolved geometry of the flow. And that's going to be important to capture this coherence property. If you know about pullback metrics, you can write this as an average of Laplace-Beltramis, where the gt is the phi t pullback of Euclidean. So the way that this dynamic Laplacian is constructed means that these eigenfunctions take extreme opposite signs in dynamically disconnected parts of the phase space. So very negative, very positive if you're dynamically disconnected. And what you do in practice is you compute several of these eigenfunctions, all the leading ones, and then to separate the individual sets, you're going to make a sparse basis for this eigenspace using sparse eigenbasis approximation. So let's have a look at a picture. So here on the left are the first 17 eigenvectors of the dynamic Laplacian. And then these span a 17-dimensional eigenspace for which you can find a sparse basis, which is shown here. So what you see in the sparse basis, this is not forced in any way, but you get these geometric blobs. And you can add them all together to get all the blobs in the one picture. And if I show you the video I had before, you see this is exactly how I construct the red in the left in this way. So you compute eigenfunctions, and then you find the sparse basis to separate the different coherent sets. So this is, in a way, a schematic for a lot of the things that you do in this area. All right, now a little bit about multiple scales. So I don't need to tell anyone here that in geophysical models, you have many spatial and temporal scales. In fact, the Zoom speaker yesterday even had a graph with log scales showing the vast range of scales that you move over. And I want to show you a couple of examples to give you a bit more intuition about how these operator methods work over different spatial scales. So in the ocean, if you're looking for disconnections in the ocean, you could do that at, say, basin scale, sub-basin scale, or down to tens or hundreds of kilometers, whatever you have resolution for. And finding these regions at different scales of connectivity, dynamical connectivity, tells you about the transport. And you're interested, of course, in transport of heat, salt, carbon, etc. So here are a couple of movies I had for the North Atlantic, and I'm going to show you first very large scale, so Gulf Stream separation. So you have this north-south temperature differential across the Gulf Stream, and then at smaller scales you have ocean eddies. Both of these are inhibitors of transport, right? So the Gulf Stream is running through the middle, and it inhibits transport cross stream. And the eddies, you can also think of transport inhibitors because they inhibit transport from inside to outside. Okay. So again, something concrete to look at. So here is some trajectory data. So the input to what I'm going to show you is just what you see on the screen, the trajectories. And you make your dynamic Laplacian like before. And what I'm showing you here is just the very leading non-trivial eigenvector. So let's say red is +1 and blue is -1, and you color the particles according to the value of the eigenvector. And what you have is a purely kinematic diagnosis of the Gulf Stream as the, on average, shortest separator of this oceanic domain. Okay, so nothing is going into here except kinematics of the particles. What's the velocity field? Yeah, it's satellite-derived of ENSO. Yeah. Yeah. And now to access smaller scales, you use more eigenvalues more eigenvectors, like in the 17 case I showed you earlier. And as you add more eigenvalues, more eigenvectors, you go to smaller scales, you pick up more irregular features, and you can access smaller objects like, in this case, eddies. So again, I'm having about, I think here, 21, 23 eigenvectors. I find the sparse basis. Each sparse basis element gives me one of these red blobs, which is an eddy, and the particle color doesn't change again. So you pick up well these pieces of the ocean that don't mix outside their little neighborhood. Okay. So this concludes my first part of the talk, which is the 0th part, a little bit of background for coherence. And so in summary, on finite timescales, you can see many spatial inhomogeneities in the data. And this is important for transport and in particular the types that are mixed less than typical regions. So these coherent sets can be used, as someone has mentioned, I think, about reduced order models. So you can use them as, they are the more predictable parts of the phase space. You could input them to create a reduced order model. The dynamical Laplacian is a very effective way of getting them spectrally. And I didn't show this, but I think all the examples I showed you, they're all low dimensional, 2 and 3D. And you can use finite element approaches that are very good for sparse data. Admittedly, all the data I showed you here is not sparse at all. There was much too much for what is needed, but you can get similar results with very sparse data. Okay, so finally, this brings me to part 1, and I think I'm good for time still, to talk about birth and death. So in all the videos I showed you, these objects were persisting for the entire time period, okay? The eddies hung around for the entire 90 days. The Gulf Stream was always there. But this is, of course, not the case, right? Eddies form and die. They can last from a month up to a couple of years. Most of them don't live much longer than a month. So how can you find when these persistent large-scale objects form, live, and die? You could, and some people have tried this, you could use methods like the ones I showed you on many, many time windows. So you have windows of different lengths and different positions in time, and you do the analysis over and over, and you try to stitch them together. But I personally find this a little, let's say, inelegant. And so what I would like to do is have a large time window in which all the action happens, and find these birth and death processes. Now, you can construct an inflated version of the dynamic Laplacian, and you can apply that, for example, to diagnose polar vortex breakup. I don't have time for this particular inflated object, but I will show you a similar one. In fact, I think a simpler one. So coherent sets, these were sets that were able to move through the phase space. So the eddies were able to move across the ocean. An even simpler concept, okay, so coherent sets, I guess, go back 16 years or so, but going back 26 years, you have a precursor, which are almost invariant sets. So these are sets that you want them to not change under the dynamics. And in contrast to coherent sets, they're really fixed in space. They can't move. So coherent sets, you want to allow the set to move around. It's a little bit more complicated and remain coherent. Almost invariant sets, you just want the set to sit there in space. And for continuous time dynamics, you can find these with the dominant eigenfunctions of the generator, which Claire there mentioned. And when you're treating time-dependent systems, this requirement that the set remain fixed in space is often too rigid. But there are certain applications where this is something meaningful to do. We're interested here in birth and death. So we want to, the set is not going to be almost invariant throughout the whole time duration. It is allowed to come and go. And so to capture that, we introduce a family again. So I have a time parameterized collection of sets. And I'll call these quasi-stationary families of almost invariant sets. So they're almost invariant. Okay, you flow them for a short time and you get the set that you had before. But you limit how much they can vary with time. So the A of t as a function of t is only moving slowly in space. Okay, so why do I care about such sort of sets? Well, as I mentioned, people use these large persistent structures as a kind of skeleton for the dynamics. Okay, so almost invariant sets, coherent sets, these are parts of the phase space that are more predictable, around which you have more turbulent or chaotic motion. So if there's some regime change, that regime change typically shows up in these large-scale sets. And so if you want to diagnose a regime change, then you can look at the persistent phase space structures and see if they are changing. If you want to make reduced order models that are crossing a dynamic regime, then you need to know how these sets come and go. And the application today is to detect blocked regimes in the atmosphere. So this is where there's no block, and then along comes a block, sits there for a while, and then it goes away. Okay, so this would fit the quasi-stationary, almost invariant definition. And I already mentioned Rayleigh-Bénard convection. It's also useful there. Okay, so a little math now. Let's say we have a time-dependent vector field V, and it has an associated SDE if I add a little noise. Then the generator for this, well, you're in this nice manifold setting with a smooth vector field, and so the generator has a specific form. It looks like this. And this is probably familiar to everyone, I guess, as the Fokker-Planck equation. Yeah, good. So if you think of F as a probability density on your space, and you want to know at a fixed point x, what's the rate at which this probability goes up or down, you're talking about partial df dt at x, and so that's given by this right-hand side. You've got your first order advective term and your second order diffusive term. So this is a linear differential operator. I'll call that g sub t. Okay? It's depending on t because the velocity field depends on t. Now what I do is make a space-time version of this. So I take my spatial domain M and product with my time interval, and now I make, well, just the something very similar called an inflated generator, but really it's a generator for the SDE on space-time with some additional diffusion in time, in the time coordinate. So you can think of it like this. You split into a spatial generator and a temporal generator. And, okay, let's say this is time, and let's say space is 2D. So I have all these copies of my space, my 2D space. And what's going on here is you pick a time, you've got your copy of 2D space. On that copy of 2D space, your generator GT acts. So it acts according to your velocity field and your epsilon diffusion on that slice. Along the time coordinate, you have pure diffusion with some strength A. And this is, the purpose of this is to tie together all the different copies of space, which would otherwise be completely independent. And you detect these quasi-stationary families of almost invariant sets as eigenfunctions of this inflated generator. So the eigenfunctions of this space-time operator will be space-time functions, and from this you get the space-time family. Okay, so atmospheric blocks, well, as I mentioned, they have this quasi-stationary property. They also have a trapping property where air is trapped. Might be hot, cold, polluted, whatever. So this is related to the almost invariance. And, well, at least as far as I could tell, we could tell in the literature, please let me know if I'm sure I'm forgetting, this is not meant to be a bibliography here of all block diagnosis research in the last several decades, but most of the work seems to capture, well, the 2D extent. By this I mean you're at a geopotential height of, say, 500 hectopascals. You get a good two-dimensional extent, but this is knowing that you have a block at a certain time. Or the method really pays attention to when the block is forming and going away, these are more statistical, but they don't give so much spatial information. Or they do a combination of space and time, but they ignore this quasi-stationarity property. And we want to do all these things at once. So we want to get a full spatiotemporal description of the block life cycle. We're going to use wind velocity. So when I talked about the V in my generator, that V is going to be wind. And what I'm going to show you is a very well-known historical heat wave in 2003. So what we will do is take wind velocity, reanalysis wind velocity at 500 hectopascals. And then we create an estimate of our inflated generator. So this is going to be for our generator, this is on a 1 by 1 degree grid, 6 hourly updates. I guess, okay, the method by which we get these generators on the time slices are roughly an upwind scheme. And so the numerical workflow is like this. You construct your inflated generator. This is without any trajectory integration. You compute the leading eigenvalues, in this case about 10 or so, and then you pass these to SIBA to separate the individual families of sets. And the one I'm going to show you, I'll show you one family that corresponds to this historical block that we're trying to diagnose. This is about the numerics, maybe I skipped that. Okay, so along the top, this is our result essentially. So earlier I was showing you these red blobs, right, that I said were the sets I was interested in. That's how it works here. So time goes across here. Each square is separated by 1 or 2 days. I don't know if probably the data is not readable at the back. And what this means is initially the block is not there, then it slowly starts to form, gets stronger, very strong, fading away, gone. This is how you interpret this, and you get the spatial extent as well. For comparison, the next row is the wind field. So you have instantaneous streamlines. And initially, you have just a westerly jet passing through. Then you start to have some kind of recirculating region, which stays in place and grows, stays in place, so you have trapping of air. You still have a recirculation here, but now it's starting to move east. And so at this point, the quasi-stationary property is failing, and that's why you tail off here. And now you've really moved east, and the block is over. At the bottom is the surface temperature anomaly. So you're slightly warm, getting warmer, very warm, very warm, very warm. Still very warm, but now moving to the east, and now you've gone really east. So I have a video which has more frames, but it's maybe harder to see everything at once. So in the beginning, you have this region that is now moving to the east. Okay. Right. Summary of part 1. So you can use these space-time eigenvectors to detect regime change, and you can track almost invariant sets throughout their life cycle. There is a similar construction for coherent sets, but this one is specifically targeted at these quasi-stationarity properties. Okay, I showed you the atmospheric block example. There is some code for this at various GitHub sites, and I have a second example that I won't talk about. Okay, so this brings me to part 2, which is about climate cycles. And what I want to do here, or maybe I should pause if there are any questions. Yeah?
So can you do the quasi-stationarity with coherent sets? I didn't quite catch.
The birth and death with coherent sets, yeah. So the quasi-stationarity is specifically for the almost invariant sets, because you want them to, one of the main properties of the almost invariant sets is they're really fixed in space.
Yeah, so I'm asking, like, can you combine those two to have finite time coherent sets that move through space, like hurricanes or whatever.
Yeah, there's a version of this. I'm not quite sure what to click to. There's an inflated dynamical Laplacian that does a similar thing. So what that would do is, if you wanted to see an eddy forming and from nothing and traveling along and then dissipating, you could get something like that. And this is specifically, what I showed is specifically targeted to the situation where you don't want the set to move. You still want to see when it's born and when it dies, but you don't want it to move in space. For this, on each fiber, you stick in the generator. For the eddy case, instead of sticking in the generator on a fiber, you stick in a Laplacian with a suitable metric. Yeah. Essentially, the dynamic, yeah.
How do you inflate a Laplacian?
Okay.
Just curious.
Yeah, no problem. So
you give it more food?
Yeah. So it's really like, what you would do is you don't do the integration. So on the teeth fiber, you put this. So you have time, and then you have these, let's say, 2D domains, physical domains. And on those physical domains, instead of putting a generator like I did here, you put this. So that's how you would do it. You don't, instead of doing the integration, which collapses across time and averages to a single copy, you just stick this or this on each separate. So for each t, you stick it on the time fiber corresponding to t. And now you have a space-time operator, and you find eigenfunctions of that.
Okay, so you inflate it in time.
You inflate it in time, yeah.
Okay.
Yeah, I should.
This is what I was missing.
Yeah. Maybe I should put. Yeah, they're all time inflated. Yeah.
Okay.
Yeah. Yes.
Maybe if I took an interval that is 0 to tau, and then I took two intervals that are 0 to tau over 2 and tau 2 to tau, and I repeated the construction for each interval, would I get something that is self-consistent?
Which one? The inflated one?
I guess the inflated one. Or does it matter where I put the origin of time?
No, I mean, it depends if something's happening at the boundary. So what you want to do is, if you know that, if you're looking for, there are some boundary effects because you have to choose some boundary conditions. So what we normally do is pick Neumann, homogeneous Neumann. But so then what you do is you just pick the interval large so that any action you're interested in is reasonably away from the boundary in time. So in your experiment, I guess it would be consistent as long as there was nothing interesting happening that you cared about at that center point.
Is it? Because if the dynamic is sufficiently mixing, I suppose, if I start at 0 and go to tau over 2, the delta g sub tau over 2 will look very different from delta. So if I start again integrating from tau over 2 to tau, maybe we can talk about this offline.
But from what you were saying, it makes sense to put everything together, and the technique will take care of identifying the smaller scales, whether in time and space. Is that correct?
You mean the non-inflated version?
Or inflated version. I mean, this is following up on Dimitri's, how sensitive is this to choosing tau?
As long as there are objects that are coherent throughout 0 tau, then it's not particularly sensitive. Okay. But of course, if you have an eddy that just lasts for 45 days, and then you do it on a 90-day interval, the non-inflated version, then you may see a kind of blurry thing or nothing much, because you're trying to find something that doesn't exist. You're asking. With the non-inflated version, you're asking, I want to find something coherent for the full 90 days. And if there's nothing, then what can you do? You won't see something that's just there for 45 days necessarily. Yeah. So in that sense, it is. But that's the whole purpose behind the inflated bit.
So your time span has to closely capture the duration of the coherent structure, or can you have a very long time and it'll capture all of the coherent structures as long as you include enough eigenfunctions?
if you're doing this average version, then the time interval should be shorter than or equal to the period on which you have something coherent. If you're doing the inflated thing, which I was saying you don't do this and you make separate fibers and now it's space-time, then it doesn't matter. Then you should be able to even see the object appearing and living and going away.
But would there be like the more objects there are, the more eigenfunctions you would need to identify them, or does it?
Yes. And the smaller the feature relative to the total domain size, the more functions you would need to get down to that scale. Yeah. Okay.
One final question, since his name appeared in your slide. How does it compare to the technique that George Haller and Veron Vera produced to identify Lagrangian coherent structures?
I think it's fair to say that both methods target similar things. At least in 2D, you can think of it as, well, it depends. I mean, George has many methods, right?
Yeah, that's right.
So if I pick the one that's closest to what this is doing, he has a method where they try to find, say for eddies, they try to find closed loops so that when they're evolved, the length of the loop remains small. I think this is most in line with what this is doing. Of course, they're doing it in phase space, so everything is nonlinear, and I'm doing it in function space, and everything is linear. So it's quite a difference in theory and method, but at least one of George's papers is similar to this, which I think is one of the better ones. Okay. Yeah. Oh, I completed this, didn't I? Climate. Okay. Yeah, so I guess there's two parts. I mean, Claire did a good job of, I'll probably rehash some of what she was doing. So first, we want to extract climate cycles from observational data. And in particular, I'm going to look at, as an example, taking the sea surface temperature and extracting ENSO. And then in the second part, which is newer, I want to compute SST perturbations that maximally either strengthen ENSO or accelerate ENSO. So now my notation changes a little bit, sorry. The dynamics is going to be T, and X is, well, I'll say what that is. I'll say it now. Okay, so I'll put a bit more on the screen. X is, let's say, the set of climate configurations. So it's this massive unknown space. And T is, let's say, how these configurations evolve over some length of time, which is also unknown. But we're going to observe these with some observation function f. So in our case, f is going to be outputting a bunch of pixels representing sea surface temperature on a grid. So if you have d pixels, then you get something in RD. This is a huge reduction, of course. So trajectories of this unknown system are going to be called x sub I. So this is just iterating t from some initial condition. And then when we observe, we'll call these y. Okay? And then you have a commutative diagram. Well, I mean, not exactly commutative, but you have your unknown system acting at the top. And then you observe. And what we're essentially doing here is building transfer operators for this observed system. So we're making some p obs, which is going to be f composed with the inverse of t obs. But we're not going to directly infer t obs in a nonlinear way. We're going to instead build p obs. And I think you'll like this because how we build the operator is extremely simple. Okay, so this is it. So you take your y as a time series. So let's say you have monthly data of sea surface temperatures. So what you do is you want to know you build the stochastic matrix. You want to know what is the probability given I'm in state I, or month I, if you like, and go to state j. So what you do is you say, well, if I were to move I forward one step, how close would it be to j? Or as I've written it here. So if these are close, then this number is small, and you have e to the minus something small, and you get something big probability. On the other hand, if you were to pull back j and it's nowhere near I, this is huge, and you have e to the minus something big, and you get very low probability. So this is just an extremely straightforward way of constructing transition probabilities. The denominator is just to normalize, so this thing is rho stochastic. Okay, now you're rho stochastic, so your spectrum is going to be in the unit circle. Just like the first part of the talk where I kept talking about dominant eigenvalues, same deal here. It's always the same thing. You want to look at the eigenvalues, in this case, closest to the unit circle, because these are the ones that are going to identify the strongest, slowly decorrelating cycles. So let me show you something with Lorentz, which you've already seen partly with, I forget who, Demetrius or Claire, one of them. And now here, T is going to be Lorentz advected by just a small time step. And my F, my observation, is just going to be the identity. So I observe all 3 coordinates of my Lorentz system. So I make that rho stochastic matrix P using the formula I had before for duration 160. And since I'm stepping with 0.01, that means a 16,000 by 16,000 matrix. And you compute the eigenvalues and you find, well, the biggest one, apart from the number 1, is here in polar form. So you see it's close to 1. And you see that every iteration, every time you multiply by the matrix, you advance around the circle 1.3%. So that means it takes you 77 iterations to get around the circle to complete a full cycle. And 1 time step is 0.01 time units. So then the cycle corresponding to this is 0.77 time units. So this is how you get cycle length from the eigenvalues. Okay, now I'll show you a movie. So on the left, you've got Lorentz, also Lorentz here. But what I'm doing is I'm coloring according to the argument of the eigenvector. So I have this 16,000 by 16,000 matrix. My eigenvector is length 16,000. Each entry is a complex number. And it's a time series. So I start at the top. And as I proceed down, I plot the argument of the complex scalar sitting in each entry. And I color according to the argument. And this is a cyclic rainbow scheme. So what you see is that you get this, what is the cycle that we're extracting here? The cycle is the rotation around the wings. And Lorentz has a symmetry to it. And this symmetry is picked up because both these wings are mapped to the same cycle. On the right, what I do is a very similar thing. I'm plotting the coloring by the argument. But as I go down this eigenvector, all these complex numbers, I simply plot the complex number in the complex plane. So this is real and imaginary. And so what you see is you go round and round like this. And the color here corresponds to the color here. The motion here is constant because you're just going around a cycle. But the motion here is not constant. So you are rectifying here the cycle in the phase space. And you see from the argument where the cycle is in the phase space. Later, when I talk about ENSO, I won't be able to make a picture like this because it's very high dimensional. But I can make a picture like this. I can still make the same, this is in the complex plane. It doesn't depend on the dimension of the system. Okay. Okay, so for the SST setup, we're using CCSM4 for 400 years, monthly. The pixel count is about 44,000. Actually, what we're doing when we construct the P is we do Tarkin's delays. So we make a vector of 12 consecutive SST images stuck together. And so actually, an observation is in R 12 times 44,000. So we make this matrix P. We've got 400 years. There's 12 months in a year, so we have 4,800 by 4,800 matrix, and we compute the eigenvalues. And this is what the spectrum looks like in a slightly strange way. So this is magnitude, and instead of imaginary part, you have frequency. So actually, maybe you can give me a little bit more because of the questions. because that would be bare 10 minutes. Okay, so what you see here is you've got the eigenvalue 1, and then the next, so importance goes this way. I mean, this is what I always call trivial. And so when I say first non-trivial, I mean whatever comes to the left of that. These complex conjugate pair, they have a frequency of a quarter, so they correspond to a roughly 4-year cycle. And we'll see that this is related to ENSO. And then less, I guess, maybe not less important, but more rapidly decorrelating as you move to the left. Okay, now in the Lorentz video, I had on the right-hand side this circle, and this is the circle that you get for ENSO. So it's not quite as clean as a circle, but it is circular, and yeah, I mean, we're in higher dimensions, and we have less data comparatively. What we do is, so the cycle is going around this way. Like sometimes it goes in the middle, sometimes it goes back out to the outside. We break it up here into 8 phases, as is somewhat standard for ENSO analysis. And each of these dots corresponds to an SST image. So to make a composite for this phase, you average all the SST images corresponding to the green dots, weighted by the radius. So if you're out here, this is a very strong El Nino, it turns out, by the way we rotated it. These are strong El Nino, these are weaker. So then you can create composites for each of the 8 phases that look like this. So you start with your characteristic El Nino, warm tongue, and then you proceed down, cooling, cooling, cold. So you're in La Nina, then you come back to El Nino. So this is your extracted cycle in the observation space. Other eigenvalues will give you other persistent cycles, just those that decorrelate a bit more rapidly. And as I think Claire and Demetrius were discussing, you can, some of the eigenvalues correspond to combination modes. All right, so now in this, yes?
So the ENSO is a little bit more chaotic than repeating every 4 years.
Sure.
Your eigenvalue seems to hit right at 0.25. Is that an artifact of the CESM4 or?
I don't know. As far as I know, this is, if you were to compute some kind of average period, then this is roughly in line with that. But I agree. I mean, we had several La Niñas in a row recently, and certainly not a perfect cycle. What we're doing is finding according to the eigenvalues must correspond a cycle. So we're finding, I guess, the best fit of a cycle to the sea surface temperature time series. Yeah. Okay, so now I want to, I think maybe 8 minutes. Now, corresponding to this matrix that I've constructed so far, I'll call this P0. So this is my, let's say, I'll call this my unperturbed operator. And what I want to do, think of this as a first-order Taylor approximation. So I'm making a family P delta where I have my 0th order estimate, and then I add on delta times what I'll call P dot, which is a derivative matrix. Okay? So delta is going to be small, and then I'm perturbing P naught by some other matrix. I'm going in some direction in matrix space. Lambda is going to be the ENSO eigenvalue. And then, yeah, by standard perturbation theory for matrices, you know that if delta is small, then if lambda is simple, you get a nice family of lambda deltas, of simple eigenvalues of the P deltas that are continuous at delta is 0. And the same thing holds for the eigenvectors, for the left and right eigenvectors. You have families U delta and V delta that are differentiable in delta at 0. And then standard arguments tell you what the derivative of lambda delta is at 0. So what I'm going to be interested in is lambda dot. So this is d lambda delta, d delta, taken at delta is 0. And you have this nice formula for it. So this is the unperturbed left and right eigenvectors. This is complex conjugate transpose. And this is the, let's say, unknown p dot, which we're going to optimize. Okay, so let's say lambda is our ENSO eigenvalue. If we can perturb p naught so that the eigenvalue increases in magnitude, this will mean that the cycle we found decorrelates more slowly, closer to the unit circle. If we can perturb so that the argument increases, this will mean that we'll travel around the cycle more rapidly, so we will have accelerated ENSO. Okay, so let's say our lambda is in polar form like this. If you take a log, you get this, and so increasing the magnitude is equivalent to increasing the real part of log lambda. Sorry, there's just some math, I guess, but and increasing the argument is equivalent to increasing the imaginary part of log lambda, right? So obviously making the magnitude bigger means increasing this part, and the angle bigger means increasing this part. Okay, so let's concentrate on the real part. So what I want to do is perturb. Using p dot, I want to perturb to make the magnitude as big as possible. That means this as big as possible. That means I want to maximize d, that thing, d delta. And you can do some calculus and use this formula. And anyway, you can compute that d real part log lambda delta, d delta, delta 0 is given by this. Lambda is known, u naught, v naught are known. P dot is going to be the unknown. So we want to find the p dot that maximizes this derivative. So we have this optimization problem in matrices. We want to maximize this expression subject to a few constraints. So let's see. Going down here, p delta is rho stochastic, p is rho stochastic. That means p dot must be rho sum 0. That leads to that expression. What we're doing here is really, if you like, you're in the space of matrices, you take the point p naught in that space, and we're optimizing in the tangent space. And so you want to optimize over a unit ball in that tangent space, and that's what this says. It's just the Frobenius norm. And then for various reasons, you might want to disallow perturbations in certain transitions, which is what this would do. Okay, this optimization has been done before in the context of mixing for dynamical systems, and what we're doing here is extending it to the observational framework. There is an explicit formula for this, which I won't put up, but it exists. It's not very complicated. You can find the optimal p dot. So this is our spectrum you've seen before for p naught. And now what I'm going to do is solve. So I solve this problem, and I get an expression for p dot. Then what I do is I take the p naught, I add on delta times this p dot for some small delta. And then I recompute the eigenvalues. And then you want to know what happens to this ENSO eigenvalue here. Well, this is it here. And what happens is it moves to the right, almost parallel to the magnitude axis. And this is just what you wanted. You wanted to increase the magnitude. So it increased the magnitude, and it didn't do much with the frequency. If I go back and replace this real with an imaginary, and I resolve for a different p dot, and I add a little bit of the p dot to the p naught to make a new p delta, and I recompute the eigenvalues, I get this. So I've increased the frequency, and it didn't pay attention to the magnitude. So mathematically this is nice. At the eigenvalue level, you get what you want. But what's really interesting is what happens in the observation space. So our main aim is to show what happens in the observation space. So what we do is we form a data matrix, capital Y, where, sorry, I'm going a little bit over. A data matrix Y, where you start at time 0, and then this is time 1, this is time 2, so this is my 44,000 pixel SST values, so time 0, 1, 2, etc. And if I multiply that matrix by p delta, then what I'm doing is forward evolving one step of my Markov chain, the observations. Okay, well, I could do that for P delta, and I could do that for P naught, and I could divide by delta and take the limit, and by definition, this would be P dot times y. And so you can think of this P dot y as the derivative with respect to delta of the one time step evolution of the array. Or, more specifically, the ith row of this thing. This is the infinitesimal delta response of observation yi. So I'll call that y dot I, and I can collect up the observations and the y dots, and I now have my optimal response vector field, which we can now visualize. So this is my second or third last slide. Here you've got the what I showed you before. This is the extracted cycle. And these are the p dots for the magnitude perturbation. So what is the SST perturbation you should do to strengthen ENSO? And I guess the thing that jumps out at you is that it's pretty correlated with the left and the middle columns are pretty correlated. So how should you perturb? If you're in El Nino phase, well, you make the water more warm in that area. And if you're in La Nina phase, you cool it down. Okay, perhaps not too surprising. However, we were happy to see that this is doing what we think it should do. For the frequency perturbation, what you see is you kind of shift ahead two phases. So these two guys here are roughly what you see here. So you want to speed up what you do is you give it a cooling kick a quarter cycle ahead. And similarly, this guy here has been wrapped around and pushed up to here. So you shift you shift this essentially up to get this, very, very roughly speaking. So you want to speed up your cycle, you give it a kick a quarter ahead. Now, just to give a bit more detail, what I'm going to show you is we have the Nino 3-4 box, and we average temperature over the Nino 3-4 box. We do this monthly, so this is month on the bottom. Black is the ENSO cycle, so you see this characteristic rapid fall off from El Nino down to La Nina, and then a more gradual recharge back up to El Nino. The green is the magnitude perturbation, which is actually more like a sine wave. It's more symmetric than, and we think, well, we have some theory for why this might be. And the red is the frequency perturbation, where you're trying to accelerate. And so you can more clearly see here that this is a quarter cycle shifted. Again, a bit more symmetric, like a sine wave than the ENSO signal itself. All right, so now let me just sum up. We can extract climate cycles from single time series. The eigenvalue gives you the average cycle period. The eigenvector shows you where this cycle is in observation space, high magnitude of the eigenvector, and the cycle phase, argument of the eigenvector. There is some theory to say that in idealized settings that actually what I've been showing you, these cycles and the eigenvectors are, through linear response theory, very robust to perturbation. And in the last part of the talk, what I showed you is that you can port this optimal linear response theory to cases where you're doing things with observations. And while my magnitude and acceleration may not be so groundbreaking for you guys, I'd be happy to hear of other sorts of cycles you want to look at and questions regarding perturbations. What we have in mind next is what sort of perturbations would, for example, favor a Central Pacific versus an Eastern Pacific ENSO. Thanks.